This week we have Richard Schwartz speaking to us about continued fractions and the four-color theorem.
Right. Okay, great. So anyway, here's a plan for the talk. I mean, I'll explain these things, continued fractions, four-color theorem. Maybe I won't go in as much detail as I did in this kind of popular talk or something. I'll say a word about the Einstein Integers. I'll talk about certain kinds of triangulations. And so, I mean, this was kind of a project that I've kind of nursed for a long time. And every time I teach graph theory, I get interested in experimenting with the four-color theorem. So I wanted to look at what solutions to the four-color theorem look like on this special family of triangulations, which are triangulations of the sphere where there's at most 6 around each vertex. And these are nice because they come in sort of some nice families. My former advisor, Bill Thurston, wrote this great paper called Shapes of Polyhedra, where he kind of explained some connection between these triangulations and geometry. So I'm going to talk a little bit about that too. And anyway, okay, so continued fractions. Okay, so here it is. You take a number like 3/7. So start with a number between 0 and 1. Take 1 over the number, and then subtract off the integer so that you get back between 0 and 1, and then repeat. So this is the continued fraction expansion for 3/7, and then here it is for 7/10. So once you get to 3/7, you just continue. Okay. So here's another view of continued fractions. This was in the other talk. I had a chocolate bars to illustrate this. But what you do is you take a rectangle that's 1 by, say, 3/7, and then you cut out as many squares as you can. So you start by cutting out these 2 green squares, and then you cut out these 3 blue squares, and then you see you get 2 and 3, and those are the numbers in the continued fraction expansion of 3/7. Here I've shown the same thing for 7/10. You get 1, 2, 3. And this is just a geometric reinterpretation of the original thing. Another way to think about it is you can think of these rectangles as being the vertices of a rooted binary tree, and the operation is you just remove one square at a time. So if you start at 7/10 and you remove the square, you get the picture for 3/7 and so on. Over here in the corner, I've illustrated the kind of little rule that shows you how the tree is constructed. You can start with any fraction. You can just kind of flow down to 1 over 1. And this is another view of continued fractions. It's this map that takes you down 1 is called the slow Gauss map. Any questions so far?
The slow Gauss, what was that?
Slow Gauss map.
Map. Yeah.
Yeah. The Gauss map is like x goes to 1 over x, integer, decimal part of 1 over x, and this one, you take 1 over x, and then you just subtract off the integers 1 at a time until you're back between 0 and 1. And that's what this thing is doing.
Thank you.
It's not called the Faraday tree or something like this?
I mean, I think this is a little different than the fairy tree. It has some other name. I can't remember the name of the tree, but it's a different name.
Thank you.
It's closely related. Okay, four-color theorem. So maybe this needs no introduction. Here it is. You can. This is supposed to be a graph of the regular dodecahedron, with the blue supposed to be just the outer face, and then you can color it 4 colors. Okay, there's it's a computer-assisted proof so far. Here's the dual version. The dual version is just you have a planar graph, and you can color the vertices 1 of 4 colors so that adjacent vertices get different colors. And for this version, you can see that you might as well just do it for triangulations, because if you have something less than a triangulation, you can just add edges. And if you can do it for the triangulation, then you can just snap off the edges. So the next slide is the first kind of, oh wait, okay, well, never mind. I mean, there was some stuff about the proof of the 4 and 5. You know, I won't explain how you prove the 6 color theorem. And I only have 48 minutes, so I'm not going to explain this nice argument that you can prove the 5 color theorem and the 6 color theorem. So I'll just skip that. Here's a geometric view of here's another way to think about the 4 color theorem. If you the tetrahedron obviously has a 4 coloring. And then if you had a 4 coloring of your triangulation, you could map the sphere to the tetrahedron by just mapping each triangle to the triangle that has the right coloring. And you can then color the faces of the triangulation black and white according to whether or not this map is orientation preserving or orientation reversing. So another way to think about it is that if you look at 2 adjacent triangles, like you maybe you have yellow, blue, and green, and then you have a choice for the 4th for this color. You either make it the same as this one or different. And if you make it the same, you color these triangles different colors. And if you make it different, like here, you color them the same color. So the black and white interface would mean like this map to the tetrahedron is folding back, and the same color would mean it's just wrapping around. So there's a condition if you have this kind of map, it has the property that around each vertex, the number of black minus the number of white triangles is divisible by 3. And the reason is because in the regular tetrahedron, there's 3 triangles around each vertex. And if you start looking at what your map does around a vertex, it has to wind an integer number of times around. And so when it's going backwards by 1/3 whenever it is black, and it's forwards by 1/3 when it's white. So in order to get an integer winding number around each vertex, you have to have black minus white is divisible by 3. Conversely, if you have a black and white coloring of your triangulation, which has this property that around each vertex, black minus white is divisible by 3, then you can just start building this map to the tetrahedron, and locally there's no obstruction to doing this. And then so you get the map, and then you can just pull back the 4 coloring of the tetrahedron. So what I'm trying to say is that a 4 coloring of the vertices of a triangulation is completely equivalent to a 2 coloring of the faces that has this mod 3 condition around each vertex. So the reason why I like this formulation is because it sort of opens the door to thinking about like a kind of a temperature, sort of like, how many you have one of these solutions, and how many black and white interfaces are there. So something like that. So anyway, Halloween is now past, but this actually came out of my computer program. So this is an example of one of these black and white colorings, which satisfy the mod 3 condition around each vertex. So this is well, this made more sense in the other talk when it was around Halloween. But anyway.
Did it just come out like this, or did you have to try very hard to get it?
No, it just came out.
Oh, wow.
I mean, all I had to do, so my program will allow you to change the vertex at infinity. So I had to change the vertex at infinity before I saw this. So Okay, I'll show some pictures in a little bit. I'm gonna activate the program and show you what it does. So I want to say a word about Einstein integers. So you have the usual triangular grid in the plane, and if you make the edges unit length, then the vertices all have the form P plus QA, where P and Q are integers and A is the sixth root of unity. Number theorists often use A squared for some reason, but they call it omega equals A squared. But anyway, and if you look at the Einstein integers in this yellow sector, they have the form positive plus positive times A. And you can just think of the Einstein integers in this yellow sector. This is supposed to go on forever as rational numbers, positive rational numbers, because P over Q corresponds to P plus QA. This just gives you a bijection between the positive rational numbers and the Einstein integers. And then the Einstein integer is called primitive if this P over Q is in reduced form. So 1 plus A would be an example of a primitive Einstein integer. And yeah. Okay. So now I'm going to just say a word about my coordinate system. Like this green dot here, this is 2 plus 3A. It corresponds to 2/3. And I'm going to build a triangulation of the sphere based on this number. So what I do is down here is the origin at the bottom of this rhombus, and the green vertex is one vertex of the rhombus, and then the vertex across is another Einstein integer, which makes the bottom part an equilateral triangle, and then there's the top vertex, which makes another equilateral triangle. So this is given the green vertex, you can just automatically construct a rhombus, which is made it from two equilateral triangles. And then you can get a sphere topologically by gluing the red sides together and the green sides together. So this thing would just fold up like a taco or like a wallet. And what it produces is a sphere with 3 cone points. There's one here. These two sides come together, and then there's one on the other side, and then the one on the top joins the one on the bottom. So this sphere is automatically triangulated. It's triangulated by these little triangles, these unit equilateral triangles, and there's 6 around each vertex, and then there's 3 around these 3 special points. Like here near the green, you can see that I mean, you get, when you glue this together, you get a black and a white triangle. Even though they don't fit neatly inside the rhombus, they wrap around correctly. So what I'm showing you here, if you just cut the rhombus out of the computer screen and glued it together, you'd get a triangulation of the sphere, and it is triangulated by one of these black and white. It has a black and white coloring with this mod 3 condition. So I wanted to show you some pictures of this. So anyway, this is an important point. So I want to just dwell on this, that for every P over Q, you get a triangulation of the sphere with degree sequence, all 6s and then 3 2s. And conversely, if you have a triangulation of the sphere with this degree sequence, you can just build it out of equilateral triangles, and you'll get one of these things. What I'm showing you in this picture is something like it's something like the universal cover of this sphere. It's not quite the universal cover. It's what they would call the orbifold universal cover. What it is it's a black and white coloring of the plane, and then you have a group of symmetries, which is just generated by rotations of order 3 around the vertices of this rhombus. And then the quotient of the plane by that rotation, by that symmetry group is the sphere. And the black and white coloring is just the lift of that coloring on the sphere to the
You have to inflate it, right? I was hoping you'd say the word inflate, and then it would all become when you
well,
glue.
yeah, well, it's a topological sphere.
Yeah.
I mean, yeah. So if you make this thing, then yeah, make it out of rubber, blow air into it, and it'll, kind of puff out like a samosa or something.
Thank you. Yeah.
Yeah, exactly. So right, it's a kind of a funny object because it doesn't seem very spherical. It's it's completely flat, but it's sort of like, it's a deflated sphere.
Okay.
A topologist probably wouldn't care, but anyway, but I just want to emphasize that, so topologically it's a sphere, and geometrically it's rather different from what you'd call a sphere. It's a sort of a double equilateral triangle, but if you blow air into it, then it'll puff out to a sphere. That inflating theme will come up again. So maybe I'll show some pictures. So that's an example where it's maybe this is this 2, 3, and what you can do is when I'm pushing the button, the computer is finding these solutions. So these are various black and white colorings. For these triangulations, there's an obvious one. You just color the squares alternately black and white. But what you can do with my program is you can count the number of black and white interfaces, the number of edges where it folds, and I'll call that the fold count. And when I was in Rutgers and giving the talk, I learned that this is called Glauberman statistics. But what you can do is you can sample by bounding the fold count. So here the fold count is 72. It's 43, but I'm going to lower this. So I'm just going to show you. So as I'm kind of lowering the allowed fold count, and you're starting to see like bigger regions that are all black or all white, and that's because I'm not allowing as many fold lines. So here I'm lowering it even lower, and you're starting to see prettier pictures. I forget what the minimum is. I'll try to find it. So this is getting close to the minimum.
So you keep the 2 + 3a cell fixed the whole
Yeah,
time?
I keep that fixed. And let me say what my computer is doing. I mean, it does like hill climbing. So what that means is that it makes a random guess, it records the error, it's probably not going to work. And then it sort of randomly flips some of the colors, and then it recomputes the error. And if it does better, it switches to the new coloring. So in this way, this particular, I'm going to explain a better algorithm later. I mean, this thing doesn't really work so well. For 2, 3, it works like a charm, but so now I'm lowering it even more. I'm down to 23. Maybe 23 is the minimum. Now it's just searching and it can't find anything. But if you go up to 23, so that thing, so I got interested in like what are sort of the minimal, what are the sort of the ones with the minimal fold count. And if you try this for a bigger guy, I mean, it may not stop. I mean, you know, okay, it found one. Yeah, okay, so it's finding them. There's a better algorithm. So this is a different algorithm, which is producing this kind of nice picture right away. So first, so now I'm gonna, so anyway, you look at these pictures for a long time and you notice something. What you notice, let me make this even better. You see a kind of a flower pattern. So this is like the only thing I really accomplished in this project. I noticed that this flower pattern always works. So I'm now going to explain how you get one of these solutions that looks like this for any rational number. And then after I do that, then I'll talk about more general things. So
before you go on, each of these configurations correspond to a coloring, a forecoloring of a graph.
Yeah, that's right. They all satisfy this mod 3 condition.
So it's not counterintuitive. Here you only have 2 colors, right?
Yeah, well, that's what I was saying. This maybe the intuition is you have 2 colorings, but you also have this additional congruence condition.
Oh, yeah.
And so it sort of carries the same information.
Yeah. Beautiful.
So all right, now I'm going to construct these special flowers that I was talking about. So this is what I mean by a trapezoid necklace. So the side lengths of this trapezoid are 3 and 5, and this would be the thing that corresponds to the number 3/5. And if you lay this thing down, what I've written here, these numbers like 3 + 5 alpha, 3 + 2 alpha, these are the coordinates of the vertices. And if you put this thing down in exactly this position, then you can put 6 more down or 5 more down, and you can get this nice necklace-like picture. And this will work for any P over Q. So that's a trapezoid necklace. Now, once you have a trapezoid necklace, it sort of the black one, like it entails the smaller one. Like here I started with the black 5/3, and then now I've produced this white 2/3. I go from 3/5 to 2/3. It's a little hard to articulate what the rule is besides just saying it, look at the picture, but basically each of the white ones shares one edge with each of the black ones. I mean, each white one has one edge in common with a black one and another edge in common with the adjacent black one. So if you look at this picture, you can imagine doing this for any trapezoid necklace. So here I've indicated this by an arrow. 3/5 entails 2/3. Now, it turns out that two different necklaces entail the same necklace. So here this black one entails the white one, just as I drew before, but this blue one, if you continued it all the way around, it would also entail the white one. So not only does 3/5 entail 2/3, so does 2/5. And if you look at this rule, turns out to be exactly the rule for continued fractions. So this is like another implementation of continued fractions. So if you organize all of these necklaces, you could think of making a rooted binary tree where there's one node per necklace, and then you join them by edges by this entailing rule, then you get the binary tree associated to continued fractions, and then this entailing rule is doing the slow Gauss map.
It's a rooted tree, so it stops after a while. You can't.
Yeah. I'll show you. Yeah. Here we go. I mean, so this is where it stops. This kind of inner thing is like 1/1.
Yeah. Right.
So this is the empty 3/5 flower. Here is the empty 3/7 flower, and you can actually see the continued fraction in this. If you, here I've kind of joined like these two trapezoids want to fit together to make a bigger trapezoid. And likewise, so do these. And if you count the number of stripes here, there's 2, and here there's 3. And this, in fact, gives you the continued fraction expansion. So this is sort of another way to see it. Here's here it is filled in. So I did 2 things to it. First, I put in this biohazard pattern in the middle, and then I took the convex hull and I just made the outside white. So this is a regular hexagon, and everywhere in sight it satisfies the mod 3 condition. So you take this thing and then you can tile space with it. And when you do that, just you tile space by translation. So when you do that, the outer edges fit together to make parallelograms. And then not only do you have the mod 3 rule everywhere, you also have the symmetries that come from the trapezoid. I mean, that come from the rhombus. So this is my construction of the 3/5 coloring. And in general, you take a P over Q tiling and you do this thing, and then you fold it up and then you inflate it, and then you get a 4-color solution. Now I'll show you a really nice picture. Oops, sorry. I'm trying to open the right program. Here we go. Okay. Anyway, this part of the talk isn't really mathematics, but I just want to show you this picture. So this is 32 over 41. And then this is 33 over 41. I mean, so what I'm doing now is I'm keeping the denominator fixed at 41, and I'm sampling the numerator. And then, of course, here it is animated.
Do you ever fall asleep watching this?
Yeah, right. So anyway, so this kind of, this thing kind of gives you a feel for it. Like in this example, like there's kind of lots of fold lines. And so this fold count isn't so good. But if you pick a number like the ratio of 2 Fibonacci numbers, then you see this really, really beautiful picture. Somehow, and then somehow this thing. So like, anyway, this thing sort of seems to have like the lowest fold count for its size. Okay, so
are you using them as a screensaver on your computer? They're beautiful, or you can manufacture them.
Yeah. Okay, well, anyway, I worked out a few basic properties of this thing. So suppose F is the number of black and white edges. That's this fold count. Then if you have a sequence of rationals converging to an irrational limit, then this capital F is the number of triangles. So somehow this is saying that all of that the fold count is going to 0. So at least sort of you're getting like lots of big regions. And then if you have the continued fraction approximants of a quadratic irrational, what that means is you take the continued fraction expansion of the number and you cut it off after the nth stage, and then you look at the rational number that has that for its continued fraction, and then that's your Pn over Qn, and then you can actually look at the fold count squared over the number of triangles, and this turns out to have a well-defined limit. I would call this the isoparametric ratio of a quadratic irrational number. It's sort of like the fold count squared over the number of triangles. And well, I did some calculations for the when you look at the ratio of Fibonacci numbers, this isoparametric ratio goes to golden ratio to the 6th. And I conjecture this is asymptotically best. If you take any of these triangulations and you take any solution to the 4-color problem, then if you let the number of triangles go to infinity, then you're never going to beat golden ratio to the 6th. So this is like an isoparametric inequality for these triangles. I want to emphasize I haven't proved it. I just I don't just mean this for these special flower ones. I mean for any possible 4-coloring, any possible black and white coloring with this property. The number of fold lines squared over the number of triangles should be asymptotically greater than the golden ratio to the 6th. That's my conjecture. So I did some numerical experiments, and if you take root n minus the floor of root n, that will give you a number between 0 and 1. And I computed this isoparametric ratio. It always is a number that's in the same field as the same quadratic field as root n. But I don't know much about these numbers. Anyway, maybe they don't mean anything. Okay, so in the last, I guess, 17 minutes, so this is a particular kind of triangulation. It's now I'm going to talk about slightly more general things. So I'm going to talk about triangulations of maximum degree 6. So the previous ones were examples, but now this is more general. So if you build the triangulation out of equilateral triangles, then the metric space, what it is, you get a metric on the sphere, which is flat everywhere except at a finite number of points where there's a cone angle. And the cone angle, it just depends on the, if 5, 4, 3, 2, or 2, the fewer the triangles, the sharper the cone. And what I've drawn here on the right is a way to build one of these things. In this example, it will have 6 points where there's 4 around and everything else where there's 6. And the way this works is you fold up the edges according to the pattern. So for example, this 2 edge glues to this 2 edge and it creates a cone angle with 4 around. And likewise for 1. And if you think about it, you look at this thing and you say, well, this polygon here has 10 vertices. And so you could think of getting a triangulation like this by specifying 10 complex numbers that are also Einstein integers. But that won't do it because there's some dependency. Like once I specify this one and this one is forced by the condition that when I glue it up that you get 4 around. So some of the vertices are dependent on other of the vertices. And it turns out that there's 4 vertices, which you can pick 4 vertices, and the other ones are dependent on those. So it's really a point in C4 will produce, if you glue it up, you'll get a flat cone metric on the sphere, which has the same cone singularities as the regular octahedron. And if you happen to pick the points so that they're Einstein integers, then this thing will support a triangulation by equilateral triangles. So this was Thurston's point of view, that somehow you have this kind of larger moduli space of flat cone structures on the sphere with prescribed cone angles. And then certain of the points, the sort of like Eisenstein points, correspond to the triangulations. So this is what I was saying in the beginning, that these things come in these nice families. So let me show you some pictures. So here is this picture here. Let me just so I can move these 4 vertices. Can you guys sorry. so on one side, I'm showing you the polygon, and on the right, I'm showing you the polygon, and then on the left, this is a drawing of the triangulation you get. It's a nice embedding in the sphere. What I do is I fix the outer 6 vertices, and then I take the harmonic embedding. So every other vertex is the average of its neighbors. And you can sort of screw this thing up. If you go too far, it will just be garbage. So these coordinates, these 4 complex numbers, I would call these Thurston coordinates on the space of these triangulations. And if you want to realize every possible triangulation or every possible point in this moduli space of flat cone spheres, you have to pick other combinatorial patterns to glue, but these give like local coordinate charts. Then you can push a button, and this thing is searching for a solution. There, it found one. This program is now much smarter than the previous one. What it does is when you have one of these triangulations, you have local types. I mean, for here in this little window here, you could have 6 white ones or 6 black ones. You could have a black and white pattern like this. You could have a pattern like this. You could have a pattern like this. I kind of sample through the different possibilities, but basically these are all the types. And my computer will even let me sort of forbid certain types. Then what the computer does is it makes a tree, and it orders the vertices in some order, and then it assigns a local type to a vertex. And then it moves to the next vertex and it assigns another local type. And if it ever sees an incompatibility in the definitions, it cuts off that branch. And so in this way, it does a depth-first search with pruning through the set of local type assignments to the vertices. And I've ordered the local types to be more solid in the beginning. So this thing tends to find automatically the more solid, the things with smaller fold count. So I'm going to come back to the program in a minute. Here, I'll just say what I said before. There's Thurston coordinates. You have the independent variables. It's these yellow points. Then you have the dependent variables. And then this gives local coordinates on the moduli space. There's more structure. It's a totally beautiful thing. If you have a triangle in the plane with vertices 0, z, and w, then this gadget down here computes the area of the triangle. And if you have a more complicated kind of polygon, then some more complicated sum like this will compute the area. And if you look at this, the area in the Thurston coordinates, basically what it is it's a Hermitian, the area is the diagonal part of a Hermitian form. So this thing's like a dot product, except instead of just having v dot w equals w dot v, you have v dot w equals the conjugate of w dot v. That's what a Hermitian form is. And the Hermitian form turns out to be of type 1n for whatever the dimension is. In this case, for the octahedron, it would be 1, 3. And what it means is if you look at these flat cone spheres up to scale, if you just scale out by similarities, then what you're doing is you're taking a complex vector space and with a Hermitian form of signature 1n, and you're modding out. Now, if you might remember from special relativity that if you do this for like R3 with a quadratic form of type 1, 2, and you quotient out, you get the model of the hyperbolic plane. And if you do it in 1, 3, you get hyperbolic space. So if you take these this moduli space of flat cone spheres up to similarity, it has a natural complex hyperbolic structure. It's just like the real forms of type 1n give rise to real hyperbolic space, the Hermitian forms of type 1n give rise to complex hyperbolic space. So what it's a beautiful picture because there's like the biggest piece, which is like the ones which are in the same stratum as which have the same cone angles as the regular icosahedron. this thing has, 12 cone points. And so this thing is like a complex hyperbolic manifold. And then you can go to the boundary in this thing by merging two or more of the cone points. And so you'll go to kind of like a sort of an edge, like a corner of it. So all of these flat cone structures are organized into one stratified space. And you could think of it as like a cube. A cube is like a stratified space because you've got the interior, and then you've got the faces, and then you've got the edges, and you've got the vertices. And in general, a stratified space is like this. But in the case of these complex things, each stratum has codimension 2, or real codimension 2 in the previous one. So anyway, all possible. Anyway, this is not so relevant to what I'm doing, but there's just this is why I was interested in these triangulations. There's this beautiful moduli space. It's even better. This moduli space is I won't. Okay, there's more to say.
What
The
about
whole
1, 9?
moduli space.
What about the space 1, 9? That might
Yeah,
be
that's the one. That's the granddaddy, the big daddy. That thing is the quotient of complex hyperbolic. I guess it's 9 space when you mod out that by a lattice. It's actually a ball quotient. It's complex hyperbolic orbifold, and the lattice is one of these famous Deligne-Mostow lattices.
It's the E8 lattice, right?
It's something like that. I mean, I guess maybe the cusp. Yeah, maybe on the cusp. But I mean, okay. It's not quite the Euclidean space E8, but I think anyway, it's a beautiful story.
Yeah.
I only have 6 more minutes, so I'm going to show you some more pictures. So let's take this solution, and what I'm going to do is I'm going to copy it into a new window. Oops. Okay. Yeah. So check this out. So this picture in this new window is it's the same as the picture on the left and the right are the same. I mean, the one on the left is just a different gluing pattern for the same triangulation, but the one on the left is nicer because the pieces don't slop over the boundaries. So the way I think of these things is like, so this is some kind of black and white coloring of the sphere, and you might wonder, like, is it like flexible? Like, can you get other, can you just sort of vary the shapes of these things and still make it glue together? And I'm going to see if I can do this. Let me pick a simpler. I'm gonna pick a simpler one just because in the interest of time. Okay, so let's try that. Okay. Okay, so here's a copy of it, but now check it out. I mean, you can continuously deform the shape. Oops. Well, if you go too far, it breaks. But the moduli space of these as you vary the shape, you don't always get triangulations, but the space of deformations is 4-dimensional, 4 real dimensional. So you have this kind of 4-dimensional real, or you just have a 4-dimensional vector space inside an 8-dimensional vector space. And this 4-dimensional vector space is integral. The Eisenstein integers saturate it. So every time you have a solution like this, as long as you forbid the ones I forbade with the black and white alternating, you can do a dimension count, and you can see that there's whatever the dimension of the moduli space is. Like for the big stratum, it's 20-dimensional, and you get a 10-dimensional. For every solution, there's a 10 parameter family. So So that's the other thing I've learned about this, that if you look at these kinds of black and white colorings without without these bad alternation patterns, then they come in these half-dimensional families. Whatever the dimension of the stratum is you're in, you get half-dimensional vector space. So in the big stratum, it's 20-dimensional, and you get a 10-dimensional thing. This is in the octahedral stratum, and so you get a 4-dimensional thing. So I mean, what I'm going to do next, I think I got kind of sidetracked, but there's this thing called Tutt's theorem, which is that you can you want to like decompose a rectangle into squares, and you more or less make any incidence graph you like, and then you solve some kind of electrical network problem, and you use the values of the flow to construct the side lengths of the squares. And another thing that I'm thinking about is like the circle packing idea, where if you have some kind of triangulation of the sphere, you can fit circles on the sphere which have the same combinatorics as your triangulation. And you find this thing by some kind of Newton's method or method of relaxation. So I've got the idea that you can, for these kinds of triangulations, you could really construct a lot of examples by just specifying the combinatorics and then doing a kind of flow problem or kind of Newton's method to actually make it fit. So this is where I'm going to go with this, is try to really understand a lot of the solutions on these triangulations by treating it as like a kind of shape packing problem. So I think I have one more slide, but maybe I'm done. This is all I was saying, that if you call a four-coloring solution generic if you never see this pattern around a vertex, and then call two generic solutions equivalent if they define the same shape packing up to homeomorphism like this. And then the equivalence classes of generic solutions seem to be rational linear subspaces of the moduli space having half the dimension of the total space. So I worked it out in practice. Like here's what I worked out, the coordinates in this example. I mean, you can just specify these numbers as you like, and then they're all just rational expressions, and then the whole thing just fits together. So you can specify A, B, C, and D. Well, in E and F, but there's some relation between, I think like C plus D plus B is A plus F plus C. And anyway, here's an example of an explicit description of this subspace of solutions. 48 minutes, I'm done.
Well, thanks for a great experimental talk, beautiful pictures. So Robert, this stop recording, and this ends the formal part of the talk, but people are welcome to linger and ask rich questions. I have